So, welcome everyone. I know these cinema chairs are really comfy and it's really dangerous to be in a cinema. So, but I hope, even if it's yet another AI talk, I think you've seen actually a lot of really useful and hands-on and practical talks so far. So this one will actually go beyond vector search and we'll look at the data side of things a little bit more and how can we be smarter with the data that we provide to LLMs to answer our questions, right? So I will spend a little time on the easy versions of interacting with models and RAG, but then we go into the data side and look at kind of what kind of data structures can help us here. And it might be a hint at the title. Let's see. So my name is Michael. I've been here before, and usually I'm quite active at conferences and doing articles and so on. I'm a Java champion. My latest book is DuckDB in Action. Really cool. You should check it out. It's a really fun embedded analytics database. And I also do coding for girls or coding clubs for girls at schools as well, which is really fulfilling as such. If you build applications in general, but also GenAI applications, one big question, so one challenge that people have is kind of how can you actually use your domain-specific knowledge that exists in your company to build accurate, contextual, and explainable applications, right? Not just random applications that where you go to a large language model and just use the pre-training data to answer questions, but how can you get actually the richness of the information that sits inside of your company already at the fingertips of your users, right? So, and still have explainability at the end. So I want to talk a little bit about what is possible with GenAI, but also what are the challenges, how to ground LLMs in truth, knowledge graphs and GraphRAG, and then look a little bit at the ecosystem around GraphRAG as well. There will be 3 demos. I hope we have enough time to show them all, but I'm a pretty fast talker, so it should be all good. In general, when you have a simple Hello World GenAI application, you just connect to an LLM, you send it a request, or you go to ChatGPT and generates the answer. So it basically uses its pre-training data to answer the questions, right? So there's actually a lot of information in this pre-training data that it uses there, but especially if you come to areas where there's little information in the pre-training data, like, for instance, specific knowledge from your domain or knowledge from your company which doesn't exist there, because LLMs are actually trained on helpfulness instead of factuality. So the RLHF, the human reinforcement learning with human feedback, is actually trained more on helpfulness. So like a little child, it tries to be helpful at all costs, right? Which includes truth, right? So it's one of the costs that are basically paid for it. So, and if these models would have been trained on factuality, we wouldn't be in this situation right now that you basically can't trust the answers that come back from the LLM, right? So hallucination is a real thing. The more the case, so my wife was, when ChatGPT came out, she tried it, she's a lawyer. So she, of course, asked legal things, especially about German law, right? And then she's a bankruptcy lawyer, so which is even narrower, and it spewed out complete nonsense, right? So, and then people say, yeah, my specific domain, it's basically completely useless. Yes, it's true because it's not in pre-training data, right? So, or not enough in the pre-training data. And that's why we need to do something different here. How can we get models to get better? So, on one side, we can collect a lot of data sets and a lot of example data, and we can take an existing model, especially also open source models, and fine-tune them for something. But the problem is the pre-training data will always trump your fine-tuning data, so there will always be more of that. And then fine-tuning is also more suited for tuning on certain output formats or styles of output than actually knowledge as such. Something that people do a lot, especially with prompt engineering and or the art of prompt engineering, is featured examples where you provide a number of examples of what you expect to come back or how certain questions should be answered into as part of the prompt, which then basically guides the token completion of the model to follow these examples to produce more of that or in the style of those examples. And that kind of already takes us almost in the step to grounding, because if those examples are not handwritten in the prompt but come from a data source that I can trust, which actually holds my data, then we get to grounding where you basically say, I get this data that the model uses to answer the questions from a reliable data source, which could be APIs, could be databases, other things, and provide this to the model together with the user's question, and then I get the answer for that. So that's where RAG comes into play. And it's kind of a little fun story. So I met the engineering manager of Meta that worked on the Llama team. And he told me, the RAG paper was actually like one side paper that one of their scientists published. No one was really interested in this. This was kind of a footnote in the history. And nowadays, if you talk with people that build actually GenAI application, RAG is almost like one of the most important things that we have. So which is really interesting. And RAG stands for retrieval augmented generation. So that means we retrieve real world information from a data source. We augment the prompt that we send to the LLM with this data, and then the LLM generates the answer in human language or natural language back to the user. That's what this acronym stands for, right? And most of the examples that you've seen today and yesterday and tomorrow are actually using retrieval with vector search. Some people might use relational databases as well, but the default thing today is because we have a golden hammer that's called AI. We use AI for everything, which includes search as well, right? Even if we had, for instance, full-text search before with really, complex fuzzy matching and Levenshtein distance and other things as well. But vectors are basically a way where we use all the parts of a large language model that is basically trained to represent information in a hyperdimensional space. So you basically have a space with 700 or 1500 dimensions, and then a certain word or a certain phrase is basically put in one point in this multidimensional space. And then when you want to find similar text, you basically compute the same 1500 dimension vector, and then you do a distance metric like cosine similarity or Euclidean similarity, where you say, I look at the angle, how far are these two vectors apart, or what's the distance if you do the Euclidean similarity. And this vector search is used a lot because it kind of captures the semantic meaning of words and phrases, right? So, and that's why you don't search for the exact text, but more of what is the intent of the user to find. So that means when I use vector search in my RAG application, I take this unstructured information that I originally get from documents, for instance. I chunk it up into smaller chunks so that they are like semantically coherent in itself. And then I create a vector embedding for each of those chunks, and I store it in some kind of vector index. And vector indexes are nowadays a dime a dozen. So they are dedicated vector databases, but every other database also added vector search basically to their capabilities. So you can use everything from Postgres to Oracle to Redis to Elastic to Neo4j with vector search. Doesn't matter actually anymore, right? So which is actually nice for developers. So we store these embeddings, vector embeddings in vector index. Then our user comes along, asks the question. We use the question of the user, use the same embedding model because embedding models are not compatible with each other. So you can't use a different embedding model, otherwise you won't find anything. Or you will find fun stuff, I guess. I should actually try this, what comes back if you mix and match embedding models. So actually, there's a big gap in the market, I think, for translation between embedding spaces. So if anyone wants to build a model that translates between embedding spaces, it would be really useful. Also for migration, imagine you created 10 million or 100 million document embeddings from your knowledge base or from your research documents, and then your embedding model gets deprecated by the cloud vendor. And then you have to basically re-embed all this content because the new model might not be compatible with the old one. Bad luck, I guess. So anyway, so the user asks a question. So we embed the question as well. We find in the vector space which documents, what are the top 5 or top 10 closest documents in the vector space, get them back, and send this basically back to the application, which then sends both the user question and the documents to the LLM to answer the question as such. So that's basic vector search. You've seen this already, I guess, in the last few days a few times. But it's not enough, right? So because what vector databases return to you, or what vector search returns to you, is basically a bunch of document fragments, basically, or text fragments, and a score, and that's it. So it's pretty black box in a way. So you can attach some metadata, but that's kind of underserving because, I mean, we all build object-oriented applications, right? So we have a rich domain model with entities connected to each other, and all of this stuff is not represented in the vector space or in the vector embedding as such, right? So we only use a small fraction of our data, only these text fragments, and nothing else of all the, rich data that we have. They are not as mature when you look at vector databases, so you don't have many of the security compliance features that you see in other databases. And vector similarity as such is basically textually similarity, but it's not necessarily relevance for the question as such, right? So there are other parts of the context, kind of, for instance, what project is this user working on, or kind of what is his development stack, for instance, or other things that actually determine the context of this question. And so a question, or the same question, different contexts might have different answers, but which is not captured by the vector similarity. And then the other thing is you give a big area of numbers into the search, and you get basically documents back, but it's a black box what happens inside, right? So why are these documents in these places in the vector space? You can't really explain this as such. So we should actually use other kinds of data as well, right? So data from APIs, semi-structured data, graph data as such, to augment this, right? So we shouldn't stop at the text fragments, but we should go further. I mean, we've had databases now for 70, 80 years as such, but we kind of immediately forget everything that we learned and just go back, okay, we have vectors now we use vectors for everything, right? And so I just want to remind you there's a big, technology and science of databases and data engineering that we should actually combine with these new technologies as such. So, and one of these data structures and one of these databases are knowledge graphs. A knowledge graph is actually pretty cool. So whenever you basically stood in front of a whiteboard and explained a concept or a new problem to a colleague, it's very likely that you started to draw circles and arrows, basically explaining these concepts, right? And knowledge graphs are actually really similar to that, right? So a knowledge graph is basically a connected information representation of reality. So for instance, in your company, it might be something like the people, the team, the projects, the partners, the processes that run inside of your company, and you just have a digital representation of all of these entities and their connectedness as such. If you want to learn more, my colleague Andreas did a deep learning AI course with Andrew Ng, and he explains this thing really well. But I want to use an example which is actually really meta. So we want to look at a conference, meaning Devox as a graph. So in a conference, you have certain base entities. You have a speaker, you have a session, you have keywords, you have tracks. You might also have rooms and other things. We could even add attendees and ratings as such to this conference graph. Each of them have attributes, like, for instance, speaker name, titles, links to sessions, and so on, keyword names. And you can already see here, I can also add embedding vectors to these attributes, which I then can use if I want to search for instance, speaker and sessions. And then we connect these entities with relationships. So that's basically where the richness of the graph database comes in. You don't have these isolated pieces of information, but you have all of them are connected with each other. And while this on the meta level looks like a very simple graph, actually, if you take this and import, for instance, the Devox data, then you get a graph like this. This is actually only a small fraction. So you have several speakers that have multiple sessions. Tracks have multiple sessions as well. You have keywords that are shared between sessions. So you can already imagine, if I look at sessions, by their shared speaker, keyword, and track, then I find similar sessions and things like that. So you can basically do these kind of information that's hidden in the network or in the connection. You can access this really quickly, right? And that's what you want to combine with the LLM. So these data relationships actually create patterns. So for instance, here is one pattern: a speaker or a session has a speaker, or a session belongs to a track and has also keywords. So we can use these more complex patterns to ask more complex questions. And that's also where then the context comes in, right? So I mentioned context before. So for instance, I might look for sessions based on the user question, but then I also want to fetch back what are the keywords attached to the session, who's the speaker, perhaps what other sessions did they give. So I can also bring in more of the surrounding context of the information to answer the questions from the LLM. Okay, so let's see first demo for this. So I saw that Devox has a REST API, and we can basically take the REST API here and run this, and then we get basically a list of all the sessions of the conference with speakers, keywords, tracks, and all the other things, which is really nice. So we can actually just, so this is a GitHub gist, so I put this also on the QR code, so you can actually do this yourself as well. So I basically fetch the JSON from the endpoint, and then I create sessions, tracks, session types, and keywords. What's really interesting is I was a bit lazy, and I didn't want to do it myself. I mean, I've written this kind of code like a gazillion times, but I didn't want to do it myself, so I basically just put in a subset of the REST response and said basically to GitHub Copilot, basically generate a Cypher code to import this. And it was almost correct, so as usual, I see AI developer tools as really good assistants for experienced developers. So if you know what you're doing, you can use these tools to save a lot of typing. Like Guido from Rasum also said, basically you save a lot of typing, but you still want to understand what it does. You want to verify the outputs and fix all the stuff that it got wrong, and then you can use it. But it basically still saved me from typing a lot of symbols and characters and so on. So I can basically use this, have my Neo4j database here, and then basically just run this code. And then it basically fetches the data from the, make this a little bit bigger, from the REST API and creates all these nodes and attributes. And then if I want to see what's in my database, I can just run this statement here. Let's return 200. So it basically, let's see, come on, Wi-Fi. So you see the green ones are the sessions, and then connected to the sessions are keywords, the speakers as well, and the tracks here as well, the Java track, for instance, right? And if I look now at the sessions, I have a title, I have a summary, and a description. And what I can do now in the next step is I can create two vector indexes, which I already did, and I can now run embedding generation. So basically what this does is it finds all the sessions and the speakers that don't have an embedding yet, and then basically takes the title, description, and the summary together as one piece of text, and then generates an embedding for this. Actually, let me show you what this looks like first. I'll just take this embedding function, run this here, and then we can, instead of text, we say hello devox. So it basically does a call to OpenAI, generates the embedding, I get the embedding back. So and then in the next step, I would just use these embeddings and set them as attributes on my entities, on my sessions, and on my speakers. So I've done this before already, but I can run this again. So I'm just getting the embeddings. We could take the title, summary, and description as text, and we do OpenAI API calls. Oh, we have no sessions with no embeddings, so let's remove some with as limit 10. Remove as.embedding. So now it should do at least 10 calls to OpenAI to set these embeddings again from my data. So which is really nice. So I can do this inside of my database. I don't have to go to Python yet if I don't want to, right? And then because we have a vector index in our database as well, we can actually do a simple vector search here in the database directly. So I basically have a question here. This is my user question. What's new about Valhalla? I take the user question, as I showed in the diagram. I go to the embedding model and generate the embedding for this question. Then I go to the vector index, which is called session embeddings. I get the top 5 results from this vector index, and then say I'm only interested in the ones that have more than 0.7 similarity score, because there's a lot of crap further down, basically. And then I say from this session that I got back from the vector store, I fetch the speaker and the keywords, and then if I run this all, then I should see here Brian's Valhalla talk with all the keywords, and then here's Brian Götz who gives the talk. So that's a really simple one, and then we can also do the same, and instead of returning the graph, we can actually say talks about Kubernetes and OpenShift. And then if you run this, we can actually also return the score. So we see it's 0.7, like these 0.7-ish scores are not really high. So I would probably, in real-world applications, I would see how we can get them better. The title, the speakers, keywords and summaries, and descriptions. So we can basically fetch this additional context from the database directly. All right, so that's the first demo that shows basically what this looks like as such, right? And so here's a picture for this. There's the GitHub gist as well, if you're interested. Basically, what is on here is what I just explained to you. So, and as embedding models, you can use OpenAI embedding models, GCP, Vertex AI, AWS Bedrock embedding models, and also other embedding models that have OpenAI compatible APIs like Olama or others as well. Something else that's here in the UI that I didn't show yet is we can also use a copilot to generate actually Cypher. So Mark was actually quite surprised how well ChatGPT knew Cypher as such, which is actually pretty cool. But given that the language has been around now for 12 years or so, there's a lot of content on that on the internet as well. So that it's in pre-training data. And our team is actually currently working on a fine-tuned model that we'll probably release in a week or two, which actually is fine-tuned on for generating Cypher as such. So this copilot basically gets the database schema. So what you do is for these text-to-SQL, text-to-Cypher models or calls, you basically take the database schema. If you want to be really nice to the model, you also provide information about columns or attributes, like for instance, a histogram of a numerical column or categorical values. You can spell them out, so the model actually knows what are my attributes in the model. And then together with your question, it basically takes the schema and generates the query for this, right? So one thing that the models actually often get wrong in a graph, it's the direction of the relationship. So if we turn this around, then we see actually the 10 tracks with the most sessions. So the Java track has 36 sessions, AI track has 14 sessions, LangChain 4j 12. Keywords, sorry, not tracks. And so it's actually quite nice that it generated kind of a query with an expansion, with an aggregation, order by, and so on. You can even go more complex. It gets you to an 80% level, right? So for really, really complex things, it gets you a query that's kind of in the right ballpark, but you need to fix up a bunch of stuff. But it still saves a lot of typing, and it's also a good learning tool, especially for like questions and queries like this. It works actually quite well. So from that perspective, I actually like copilots for that reason as such. So that was just a little sidetrack with the copilots. But if you now want to look into how does this work that I bring kind of the knowledge graph and the LLM together, right? So I kind of hinted a little bit at what I just ran before, where I do the search initially and then fetch additional information from the graph. But it's basically an evolution of RAG, or it's a special set of RAG patterns, right? So because if you followed like all the stuff that's happening every day, like the 10 or 100 papers and articles that everyone publishes on all kinds of AI topics, you might have seen there's a lot of topics on how can we improve on RAG, right? Because basic RAG only gets you so far, right? So there's, for instance, contextual RAG from Anthropic, the paper that came out last week, where you basically combine, for the vector search, context from the document with each chunk again. There are things like query rewriting, where the user query is rewritten into something else. There's other things where you say, can I do re-ranking? Can I do hybrid search, where I combine full text search with vector search to get better results? And there's like, I don't know, 50 plus advanced RAG patterns that people do in the different phases of the execution. And GraphRAG is basically a set of advanced RAG patterns that uses graph data structures as part of the retrieval, right? So it might be a graph database, but it might also be just graph data structures as such, right? And what this means is basically in the retrieval step, you don't just do basically simple vector or full text search, but you actually use the connected information that you have in your database to get additional information. And then the other thing that you can also do is you go beyond this and actually add additional information from the graph structures to your database, which can then also be used, but I'll go into this a little bit more. So you get more context, but the other thing that you also get is explainability. But because of the information that you fetch from your database, you actually can determine how this is fetched from the database and what is fetched as well. So you can basically say, okay, it's not this black box where I have a bunch of numbers that I send to the vector search and I get something back with scores. But because the query that fetches this additional context is basically provided by you, you can actually determine what comes back, and then you can actually trace back to kind of, if a user asks a question, I provide these sub-pieces or sub-graphs of my data to generate the answer. And the user says, yes, this was a good question. I can actually trace this back to the original pieces of information and I can re-rank them. For instance, I can increase their score to say, okay, for next time a question like this comes in, prioritize or prefer these pieces of information because in the past they also answered the question in a way like this, right? And then other things like security, so all the database security and access control is also applied. So something that you can't see, you will not see because your permissions don't allow you to read these nodes or relationships as such. So all of this is already taken care of as well. Plus you can do a pre and post filtering on these queries. So for instance, if you have additional context from the user, then you also bring it in and then you can basically say, I only want to see things that are relevant for this team or this department or for this context as such. So on one side, you have the vector search and the hybrid search where you combine it with full text search and re-ranking. So where you can basically use embedding models. And besides the text embeddings, you can also use graph embeddings. So graph embeddings are a machine learning approach where you take basically the structural component of a node and its neighborhood and turn it also into an embedding vector. And then you can do basically fuzzy graph search. So you can find, for instance, people with similar behavior or like products with similar fault exposure or something like that based on the network topology basically around them. So basically you can combine vector search with full text search for hybrid, or you can use graph embeddings as well for search as well. The other thing that's really cool is if you think about documents and chunking, right? So basically you say, okay, I have a document and I chunk it basically in smaller parts. Then you actually can take this document, and what you do by chunking is actually, especially if you do hierarchical chunking, you create a tree as such, right? You have your root document, you have your sections, your paragraphs, your sentences, and then you basically can break this down. And especially if you have structured documents, then you can create a graph for that. And then at the bottom level are the chunks, and those are basically getting then the vector embedding as well. So you can also represent the textual information. It's kind of the lexical graph as a graph data structure, which gives you a much richer way of interacting with this, right? So for instance, if you want to say something like, hey, I'm also interested in the previous and next chunk of information because there might be some cutoff where the current chunk comes back from the vector search, but there's some information that's coming before and after. So it's actually really easy to get the siblings, right? So what's the previous and next chunk? You can also say, I want to get all the chunks of this document, all the chunks of this paragraph. Then you get just one level up and then one level down, and you have everything as well, right? And there are also other things that you can do. For instance, you can connect those chunks based on the vector similarity also into a similarity graph that you can basically also say, hey, for this piece of information, what is most similar on the graph level, which you then can integrate into your graph queries or use for recommendations as well. So just by taking documents and turning them into a graph structure gives you many more ways of how you can basically query this data and interact with this data as such. Right? I've seen people doing this as well, basically in a client side where you take all this information, kind of what's the parent, what's the kind of next and previous chunk, what is basically the source, and so on. Where basically put this all into Python data structures, and then you basically on the client side you have to iterate and fetch all this stuff as well. But of course, I mean, coming from the graph world, if I can just draw a relationship between two entities, then I can just make use of them as I want, right? So I don't need to basically manage all these IDs and these IDs and these IDs and basically manage all of them. And if I then pull many documents into my graph, I get really interesting effects because then they form basically a connected network. Because most sets of documents, if they're not completely separated out from each other, actually form a connected network of information, right? So for instance, let's say you're a research organization which has a lot of medical research papers internally, right? Or research results. So if you ingest like multiple of these documents, they have overlapping things like different genes or diseases or expressions or proteins and other things that will actually connect the different documents together as such, right? As you bring them in. And then what you get out of this is a knowledge graph as such. So and in the GraphRAG part, it's basically the same RAG pattern, only that basically in the retrieval step, we use these graph patterns and the magic happens there. So we use a specific set of retrieval queries to get the information and then get that back. There are different kinds of retrievals that you can use. Basically, the simple one that I just showed, which is vector search and hypertext search plus a graph retrieval query, where you then say, okay, someone with subject matter expertise wrote this piece of query that fetches exactly the piece of context that I need for this category of questions. So you can also do something like question categorization or routing, basically, where a set of questions is mapped to a set of retrievers in the application. You can use text-to-cipher like the copilots use or the fine-tuned model can use, where basically the user question is, together with the schema, is taken into a query and then executed. Or you can also use agentic traversals, where you basically have a little agent sitting on top of your data, and it basically collects information from the current place, from the current node, and decides, do I have information to answer the user's question? If not, I can decide based on the different relationships, do I go left or right, or do I follow this lead? It's a little like a little detective almost, going around your data structure and collecting this information. So there was an interesting paper called GraphRAG, which does this approach as well, which is interesting. And there are a bunch of other retrievers that are also possible. Because I'm pretty old, and I was there when we had Christopher Alexander's patterns and design patterns. I thought it could be really interesting to capture many of these advanced RAG patterns and GraphRAG patterns in a pattern catalog, so that we don't have to reinvent the wheel again, time and again, and we have to basically explain every time, oh, this is this and this is this. So I thought if we can give these patterns names and give them like context and descriptions and pros and cons and a graph model that comes with the pattern, then we can basically create this repository of interesting information. So this is an it's an open source repository under GraphRAG, so graphr.ag. You find like many of these patterns. I think we're at 20 or 25 now, which capture all the things that I already mentioned. And something that's really interesting is for using GraphRAG, it's not enough to change it or have a different retriever. You also need to do something on the data pre-processing side, right? So because as you get the data into your database, you want to turn it into a graph, which takes me to my next section. Or before we go to the next section, we can actually do a quick segue. On a graph database, or you can also run graph algorithms, which means you can do things like PageRank, clustering, pathfinding, and other algorithms that basically run on large-scale graphs really efficiently. And you can basically use this to enrich your graph data to get in additional features, additional metrics and scores into your data that you can then use for re-ranking. So you can, for instance, say, all these documents are forming a cluster. So I want to actually, from each cluster of documents that I have, I want to have some representatives in my result as such. That's, for instance, one example. I don't need to basically fetch everything that's in this cluster because I have representatives. So I, for instance, can get certain representatives from this. Right? And so we can enrich our knowledge graph using these graph algorithms. And the last one is actually really interesting, the community detection to find related parts of documents. For me, this is almost, I imagine documents as being in like a linear flow of information. It's like a storytelling, right? You have a story arc and the document tells a story and has certain sections as such. But then if you import multiple documents or many documents into your database, then all these documents have almost create these overlapping context clusters as such, right? So because you have these kind of clusters of similar information, but they're spread out over the documents, and if you just look at the documents, you wouldn't see these kind of cross connections, but if you turn them into a graph, you basically have these overlapping contextual topic clusters. And so what Microsoft did is in this GraphRAG paper that they published in March or so, they actually did this, right? So they basically imported textual data into a knowledge graph and then ran clustering algorithms on top of this, where they said basically all the entities that we extracted from this from the source document, we run a graph algorithm, clustering algorithm on this, and then we basically get representative community nodes or communities of entities where we use an LLM again to generate a summary. So I don't need to basically look at all the fine details for answering the questions, but I can actually create an aggregated summary of each cluster of information, and then I can, for certain global questions, that's why it's also called from global, local to global, for certain global questions, I use those to answer the questions, because that's basically cross-cutting information that spans many, many documents, right? Where in each individual documents, and even if the 10 in the 10 chunks that I get back from the vector search, I would not get this information. But by looking at kind of across the documents and creating summaries, I get this basically aggregation of information as such. So that was a really interesting paper there. And here's the GraphRAG pattern that kind of goes there. So you see here on top is the entity, the document graph. Here are entities that have been extracted from these chunks, and then here the little green ones are the communities, and those are then used to answer global questions as such. Okay, does it really work? So our teams have done internal testing in eval, but also other companies like LinkedIn and data.world have done this as well. And LinkedIn has been running this now for half a year for their support organization. And they found that kind of using graph data structures to represent their support cases and all the context of the support cases actually improved several of their metrics by quite a bit. So you can find all these papers, of course, online. So we were really excited about like all these people that were not Neo4j publishing these papers about graph data structures and LLMs and so on. And so in general, I think of this as, if you look at the bigger picture, I think of this as LLMs have really good language skills, but you can't trust them with memory and facts as such. But graph databases and knowledge graphs are really good at capturing like rich, complex sets of information. And if you bring them together, it's basically like the left and the right side of the brain. So one brings kind of the language skills for interaction, and the other one brings the high fidelity connected data. And then if you put them together, then you get a lot of really cool stuff out of it. So we spent now almost 2 years kind of integrating with a lot of the ecosystem tools. So we have integrations for LangChain, Llama Index, Spring AI, LangChain for J, Haystack, DSPy. Our team has also written a Neo4j GraphRAG Python package as well, and built a bunch of tools around this to make it easy for people to get started as such. And one of the tools I want to show you now, which is the LLM Knowledge Graph Builder, because it solves for a really interesting problem. So many people that want to get started with graphs and graph databases are actually looking at a blank slate or blank screen and say, I don't know what I should do here, right? So this graph stuff looks really interesting, but I also don't know how to approach it. But fortunately, these language skills that the LLMs have are also really, really good for extracting information. So because if you apply these language skills on text data, you can also extract entities and relationships from the text data using LLMs. In the old days, people used NLP tools like Spacey or Stanford NLTK or others with a lot of like linguistic and fine-tuning and training of these models. With LLMs, you can basically use stock models like GPT-4o or Llama 3x or Gemini models. You basically give them a good system prompt. You can also provide them with a schema of information that you want to basically have extracted. So what do I care about from these documents? And then they go ahead. Fortunately now with structured output and JSON output and function calling, we get much better unstructured responses as well. So then you get basically at the end from the LLM for each text chunk, a list of entities and a list of their relationships, which is basically heaven sent for us, right? So because it saves all this way of, hey, I need to do graph data modeling. I need to write like the cipher code that you saw for me. That was actually for structured data. But for unstructured data, you first have to extract and then import, right? So that makes it much harder. So Knowledge Graph Builder was basically a tool that we built where we took our LangChain integration that has already this knowledge graph extraction as part of the integration and put a backend and frontend on top of it. And it's basically running online and you can just use it. Basically provided with PDF files or web pages or Wikipedia pages, and then you select a model, provide a graph schema, and then get going. But instead of showing you the slides, I show this to you in real. So here we have the Knowledge Graph Builder. So I already loaded a bunch of documents as such. So one web URL, one Wikipedia page, another web URL. So one of the web URLs is here this introducing Gemini post from Google. I have a DeepMind Wikipedia page here and a Google Wikipedia page as well. And then something about AlphaFold, I think. Yeah. So and basically what you do is, if you want to, you can basically define a graph model, which basically says I have these node types. I have a person, a company, a location, and a technology, and then relationships like, for instance, someone worked at a company or a company developed a technology. Or a company competes with another company, right? So and that's basically what you give to the LLM. You give to the LLM the chunks of your documents, plus this bit of schema, and then it basically goes off and you processes your information. And when you upload data into this tool, I can probably do another one. Let's say we use Wikipedia, or we had, what was it? Alpha chip. So there was this alpha chip. Sorry, this is not ARC. So I can just say I have this web page. I have here my alpha chip launch blog post. So I get a new entry here where it says new. I can pick one of the models. So I have OpenAI models, diffbot models, Azure models, Ollama, Bedrock, Anthropic, and so on in dev mode. So this is all an open source project also, right? So you can run it yourself. It's just basically Docker compose up, and then it basically runs on your own machine or your own environment. So I use GPT-4o, we use the model, and then I basically just press generate graph, and then it starts processing. And while it's processing, we can basically start looking at the data it generates. So here it starts by taking what I showed you before, the document and the chunks, and shows how they are basically connected to each other. So all the chunks are pointing to the parent document, but also the chunks are connected with each other with an next relationship. With a next relationship, but also similar relationships. So we got also chunk similarity as well. And then as this processing progresses, let's see, we actually can see that it starts to extract entities from these chunks as well, right? So it basically has 2 people, 1 location, 1 company so far. Let's see if it's more of a refresh. Let's see. So now we have more of them, so I can actually hide the documents and the communities, and then I only see the extracted entities. So I have basically Google and Veo and Gemini model and Google data centers and Gemini over there, and then somewhere is Imagen, and somewhere we also have probably the alpha chip stuff as well. All right, so we can actually see while it's processing. I think this is now done. So it extracted 147 nodes and 108 relationships from that web page. But this is basically put on top of into the graph now. And now what we can do is, I mentioned all these retrievers, right? So at least in dev mode, you can basically select, I want to have only vector search or graph and vector or local search or global search or something like that. So for instance, if I use vector search and graph and vector, and I ask a question like, for instance, what did DeepMind work on? Then it basically fires off these different retrievers to the database, and then sends these responses back to the LLM that you have selected, and then it basically shows you the responses here. And what's actually really nice about this is it doesn't just show you the response, like the final result, but you can also basically look behind the curtain, like X-ray vision, where you see actually what did go into generating these answers, because there's here this details link, which shows you these were like the sources that were used. So these were like the documents whose chunks were basically retrieved. Here we see the chunks themselves that have been used, so with the scores. Sometimes I don't really understand why certain chunks have really high scores, because they're kind of meaningless. But that's kind of the point with the vector search that I wanted to make before, right? So it's basically a black box where you pass in the vectors, you have these vector embeddings, and then sometimes stuff that you get back is actually not so relevant. But what you can also see is kind of what are also the graph entities. So what are the people and technologies that have been extracted from this? And then I can basically see and dive down in what has actually been used to answer this question as such as well. So that's where the explainability comes into play. And then you can basically, with the multiple selected models, you can basically click and compare these models. So for instance, for vector search only, you only have chunks because there's only vector search and there's no graph entities that are used as such. We are currently working on also adding eval to this, so that you can basically then also have we use Ragas as an eval framework, that you as a user can also see the different evaluation metrics on your question, basically with the different retrievers in a different context, so that it's also something more of, hey, we show you how does this actually rank with the different retrievers, and you can test it out as such. So pretty nice tool. And then, of course, because it's backed by the database, you have all this information in the database, and then you can do whatever, right? So you can build an application on top of this. This can basically be your first step into turning a pile of legal papers into a knowledge graph, which then powers another application. Or you can just use it to understand the connections between your documents better. So far, it's free to use, so my boss is still footing the bill for all the OpenAI calls and everything. So feel free to try it out and let us know how it goes. If you want to look at the GitHub, is linked here, and also documentation is linked here as well. Okay, going back to my slides here, we only look into this. This is the application. It runs online. You can just use it with a Neo4j database. And the open source project is also doing quite well. So we kind of at 2,000 GitHub stores now. So people seem to like it. And as I said, you can run it with Docker Compose, add your own models, configure your own models as well. And the core code for extracting entities is actually these few lines of Python code, which basically just take the graph schema together with the LLM that you want to use and the documents that you want to transform. And then if you have the documents that you get back as structured graph documents, we just say graph add documents, and then it basically ends up in your knowledge graph. So pretty low amount of code that you have to do as such. Yeah. The other thing that I wanted to mention is the LLM framework integrations. I already mentioned it a little bit. So we have different aspects. So with the different frameworks, we integrate vector search, GraphRAG search, as well as Neo4j integration in the first place, and then knowledge graph extraction. So if you look at the different frameworks, you see like the different ones with their level of integration yet. So we try to do more, but we have only a small team. So everything is moving so quickly, so it's quite a challenge to keep up with all the developments everywhere. But we try our best to give people the integrations wherever they want to. And it's actually good. I talked to some large companies, and they actually said, hey, we are really impressed how you're keeping up at Neo4j with integrating with all these frameworks. Even us, as one of the FANG companies, we don't have enough capacity to integrate but beyond LangChain or something like that, which I found quite nice from them to say. So my last demo is basically how can I now use this data that I extracted in the knowledge graph builder and basically access it from let's say from a notebook. So I put together this Google Notebook, and I hope that Gemini, that Colab did not disconnect. It hasn't, so which is good. So I hope you can read this. And this just shows you the LangChain integration as such. So we have a graph object in LangChain, and we can basically connect to our graph. I uploaded an end file here, so I just connect to this. And then I just can run any kind of query. So for instance, here I just look at how many entities are in my graph from the extracted document. So I have 256 technologies, 74 people, 66 companies, 41 locations, and so on. Right? So that's kind of the data that I have extracted in my database. And now I can start doing some of these kind of more LLM-ish interactions. So for instance, if I want to answer this question, which company developed Gemini, I can use the vector index that's integrated here and say basically use this vector index as a retriever and retrieve for this question the top 5 documents as such. And if I just run this, then I basically get the top 5 documents with their scores back. So you see here the score and the chunks basically as such. So that's basically just the vector search. Then of course I want to integrate this. But before you do it, we can actually ask GPT-4 to answer this question. And if I just say who developed Gemini, because the knowledge cutoff was kind of later, it says Gemini was developed by the cryptocurrency exchange company Gemini Trust. Okay, so that's not so helpful because I asked I didn't ask about models, but if I ask about models, I think it comes back with McDonnell Douglas or something like that. And then we can combine the vector search with this LLM prompt. And if I run this now, I first run the vector search with the retriever here. So we take our vector index as a retriever with top 3 documents. And then I use this context that I provided from the document here in my system prompt. in this placeholder and pass it to the LLM and get the output. And now it says Gemini was developed by Google, right? So which is coming from our database. And then I can do a vector, and retrieval query, which then gets more information as such. For this question, it's probably not so relevant, but we can probably change the question. No, I don't have enough time, sorry. We can now basically ask also more complex questions. So for instance, if I want to see, if I run this query in general, I see kind of all these patterns in my graph, right? People that develop technologies, people that partner with each other. And so I can actually see who did Google partner with, right? So which is basically distributed across a lot of documents, but in my graph structures, it's there as such. Okay, and with this, I want to leave you. If you want to learn more, we have both an online developer conference coming up in a month, Notes, which is in its 5th year, and the GenAI ecosystem pages that give you much more information about all these integrations. Happy to answer more questions, and with that, I'm good to go. Thank you, everyone. I'll probably leave this on. Cool, any questions? Yes?
Yeah, have you tried also asking LLMs about discovering relationships across a set of documents? What does it give compared to, you know in advance that, okay, companies are related, etc.? Is it interesting?
So the question is, have you also asked LLMs to discover relationships between documents? You can do this. That's one challenge, is depending on the size of your documents, how many of these documents can you fit into one context window, right? So now with 1 million context lengths, it should actually work. And then you also probably need to specify what kind of relationships do you want to see between the documents. But I think it's definitely possible. The question is this the right granularity? Because a whole document is a pretty large piece of information. And so you might get, actually every document is connected to every document, right? But you need to narrow it down to either subsections of the document or to specific pieces. And then you still don't know why and how are they connected. Do they share certain, like, for instance, let's say genes or proteins for biomedical documents, or do they share basically researchers that publish something together, right? So that's also something that you would also have to extract. But it should work. I don't know why it shouldn't work. It's basically what we do here, but at a higher level, at the document level as such. Cool, any other questions? If not, I'm still here, so feel free to find me and discuss more. Thank you.